I think it's just notation because in classical log,
Okay.
it's log something.
Yeah.
Or the other way, whatever.
If it's asking for the principal value, you want to use the principal branch of the log.
So time flies. So thanks for being here today. Let's finish the discussion about I/O devices. If there is time, I'll do floating point. Just a reminder, tomorrow I'm not in town. Mostafa will come again. I asked him to cover two things. I don't know if he's going to be able to. One is to go over stack attacks, a kind of virus that you're going to be able to appreciate how they work now that you understand how function calls work. And then on top of that, there is a lecture on code races, which deals with interrupts and what do these mean about programs that run concurrently on your machine. This may seem a little bit odd to cover, but I think it's a fundamental concept you should be aware of because no computer today runs just one program. And these kind of code races will appear even on single processor systems because of time multiplexing. Mostafa will explain tomorrow, or on multiprocessor systems. And today, pretty much every system you have out there has multiple CPUs in there. Okay, now, where did we leave off last time? We're talking about the timer. Timer is a device that allows you to measure real time. It's essentially a stopwatch. That's what it is. It's a device that allows you to set a counter. Then you ask the device to count down from that counter value to 0. And to notify you, either through interrupts or through polling, that it has timed out. That is, it has counted for the period. The board we have has two timers in it. Both of them use a real-time clock, which operates at 50 megahertz. This means it will do 50 million ticks per second. Okay. The way the timer works is you set an initial value. So step one is set init value. Then start. This triggers the countdown. Towards 0. This is going to be a positive value. You count down towards 0. And then timer notifies you of timeout. That is, the counter has become 0. Okay? So set init, so the counter gets set by some initial value. The CPU does that. Then the CPU says to the timer, starts counting. The counter keeps counting down. The moment it reaches 0, it either raises an interrupt if we asked it, or it raises a hand and says, okay, I timed out. Okay. This is the single count mode. So you set a value, the counter counts to the 0 and stops. There is an alternate mode where it's continuous. That is, you set an initial value. The counter starts, once you tell it, counts down to 0, raises its hand, then automatically resets the value to this and starts counting again. It's up to you to go and look that it has timed out. So far, so good? Any questions about this stuff? We're going to do an example to see how it works. So the counter on our system is the first one. It's at this location. That's where it's at. This is timer 1. There are two of them. They're identical in terms of the internal structure. They have 1, 2, 3, 4, 5, 6 registers. The ones that we're going to be discussing for the time being are the first 4, which is at offset 0, you have the status register. All of them are 32-bit registers. The status one really has just 2 useful bits for us, and they're both indicators. That is, think of them as light bulbs. They turn on, meaning something. You can write to this register, it has no effect. It's meant to be read only. Okay. So bit 0 is TO, which stands for timeout. In the beginning of time, this is supposed to be 0. The moment you ask the counter to start counting down, remains 0. The moment it times out, that is, it has reached down 0, it sets that. What I said before was not exactly right. This is read-only. I'll explain what I did wrong. Second one is the run. Not none, run. And this is 0 if the counter is not counting, the timer is not counting, and 1 if it is counting. Okay. All right. I just said a second ago that this is a read-only. I was wrong. This is read-write. Okay. The mode of operation is as follows. In the beginning of time, this is 0. The moment you say start counting, this goes to n, and this starts counting. The moment it reaches 0, this is set to 1. You can either have the timer give you an interrupt, or you can go and look at it through polling. We're going to do polling today. If you go through polling, you have to go and explicitly clear that. So you have to write a 0 there. Now, when the timer times out, run is either going to stay at 1 if it's in continuous mode, because it's going to keep counting again from the beginning, or it's going to reset itself. Okay. Any questions about this too? I'll take that as a no. Okay. How are you, by the way? Is everybody okay today? You're doing a lot of midterms, taking midterms? That's what the... Eh? Not yet, okay. We have to discuss the midterm later today. We'll do that. This is the status register. Okay, now at distance plus 4, we have the control register. And that guy is as follows. There are 4 bits that are relevant here. 0, 1, 2, and 3. Okay. Now, this is interrupt on timeout. If you set this to 1, the timer will raise the interrupt. And the interrupt is, I think, IRQ 3. Again, these are design decisions that the designer of the system has made. Okay. Now, 0 means don't raise interrupts. We're supposed to talk to you through polling. Now, this is 0 means single run, count down to 0 and stop. 1 means once you do that, reset yourself and count down again. This stands for continuous mode. Now, and these are really commands now. There is the start, and there is the stop. Fair enough? And you're not supposed to write 1, 1 to both of them. You're supposed to say one of the two. If you say both of them, something will happen. Again, it's undefined behavior. Something will happen. Who knows what? Don't assume that it will always be the same. Don't assume that in a future version of this hardware, it's going to be the same as it is right now. That's what it means, undefined behavior. So far, so good? Now, if you haven't guessed it, the last 2 registers are the ones we're going to be using to specify where do we count from. What's the initial value? And these are 32-bit registers. However, they're funny the way we use them. So a distance plus 8 and a distance plus 12, you have 2 registers. One is called period L for low, and the other one is called period high. Both of them are 32-bit registers. Okay. However, only the lower 16 bits are in use. And this would be the low, this would be the high part. The actual value you're asking the counter to count down from is the concatenation of these 2 lower parts. All right. Again, for the time being, let's not concern ourselves why it is like that. This is the way it is. There are 2 registers. The 32 bits, however, 16 of them are only useful. The rest are useless. So for both of them, it's only the lower 16 bits that are useful. they are meant to be interpreted as a 32-bit number together. The lower 16 bits of that 32-bit number come from this register, and the upper 16 bits of that value come from this register. Okay. The device does that internally. Okay. Now, if you care why this is done, because it simplifies the hardware underneath. If you look at these registers, even though they are 32 bits, we only use values that are relevant to us in the lower 16 bits. So it turns out that when you actually build this thing, it is much easier to build the hardware to connect these two news. That's what it is behind it. Yes?
And when you put them together, what is this supposed to represent?
A 32-bit number. And that 32-bit number is this. You're counting down from that at a rate that is 550 megahertz. So there's going to be 50 million ticks per second. You give me a value. If that number, for example, happens to be 50 million, then you're going to be counting for 1 second. It's going to, if it's 100 million, 2 seconds. Okay. Fair enough? That's what it is. Ta-da. Alrighty then. So let's write now a function so we see how we're going to use that. Let's call that function, I don't know, wait a second. Okay. And actually, let's not make it this wait a second. Let's make it wait some seconds. So it's going to get an argument, which is going to be R4. And it's going to say how many seconds you want this to wait for. OK. Alrighty then. So the equivalency will be wait a second. It takes an integer, which is the number of seconds to wait. You call that, it blocks you for this number of seconds. Alrighty. First thing we got to do, we got to get the timer into a well-known state. So let's get a pointer, move A, let's say R5, 0xFF20 2000. So we get the base of the device. Next thing we want to do is we want to stop the counter. Movie R6, let's say. So 1, 2, 4, 8, right? Store word IO R6 4 R5. Okay, what does that mean? The control register is a distance plus 4 from the base of the device. We're going there and we're writing a value that has only 1 bit set, and that happens to be at this position. Everything else is set to 0. What does this thing do? It resets the the timer. Okay. Now, I don't know whether that's really needed, but how about we do a store word IO R0 0 R5. Again, for this one, please double check it in the lab whether you actually need that or not. I don't remember at the moment. This also clears the intention here is to clear the timeout flag. But I think stop does that anyhow. So that's why I have this in question mark. If the TAs give you a hard time if you put this in your lab, just say, my professor Andreas said so blame him. Okay? So far so good? Next thing we want to do is we want to count seconds. So they give us an argument. I'm going to do a double nested loop. The inner part of the loop will be counting 1 second. The outer part of the loop is going to be counting seconds. So I need a constant here that will allow me to count for 1 second. So somewhere in the code, I can say the following. .eq. Normally, you will put this outside the function. Okay. Let's call this ticks per second. All right then. What did I define? I define from this point on, anytime I use this label, this sequence of characters, this will mean 50 million. It's just text replacement. It's a macro. Everyone okay with this? All right. Now here come two interesting pieces of code. Give me a second and I'll explain what's going on. Okay, now, notice, let's look at the last instruction. This writes to a register that's a distance plus h. That happens to be period low. Okay? What am I writing there? I'm writing a constant. What is the constant? I'm missing one argument here. The constant is R0, 0 plus some immediate. This percent law, it's a macro that exists inside the assembler, is so that you can extract easily parts from constants. This says take the lower part of this value, whatever that value happens to be. In this case, that happens to be 50 million. So it converts this to the binary representation in 32 bits and takes the lower 16 bits. That's what load does. Right. It's just a convenience mechanism. This means write this down in binary and take the lower 16 bits of that representation. That's what it means. It's all syntactic sugar. That's all it is. It's a convenience mechanism for us to be able to write code like that. Could you do this otherwise? Yes. You can write this in binary on a piece of paper. You can take the last 16 bits and write those in hexadecimal. You're done. It's the same thing. It's just rather than you having to do manual labor, it allows you to do it with a few more clicks, which is again manual labor but doesn't require any thinking. So far so good? Next sequence will be Ri, R6, R0, percent high, ticks per second. So if you haven't guessed it, this takes the upper 16 bits of the binary representation in 32 bits. And we're going to do a store word IO R6, 12, R5. So now this has set period high. So we have loaded the period registers with the 32-bit constant that represents 50 million. That's all we care about. I'm going to continue my code here. Next thing we're going to do is we're going to start the timer now. Right, 50 million, let's start it. So this goes underneath that movie. Now 6 is the following in binary. So we're going to be setting start and continuous mode because we want to be counting a lot of seconds. Okay. So we're going to have it start counting 1 second, and then we tell it once you finish counting, please count the next one. We're going to have a longer discussion why this is better to be 6 rather than just 4, which is just count 1. Then let's go and wait for 1 second. What we're going to be doing now is we're going to be keep asking the timer, did you time out? Did you count 1 second? So we're going to be doing a load word IO R6. Oh, maybe I should actually write it somewhere. Store word IO R6 4 R5. So now the counter starts. Sorry, I forgot to say that. I created the constant, but I forgot to write it to the control register. Okay. So now the counter actually starts counting after this instruction.
Does the movie only take one argument besides R6?
Yes. Absolutely. And now we go and we wait for 1 second. We're going to use polling here. Should I wait until everybody has reached this point? We're good? Okay. So now from this point on, we're going to be reading the status register and saying, did you time out? Did you time out? Did you time out? That's the thing. So we're going to be saying load word IO R6 0 R5. So we're getting all the bits here. We need to keep just the last one. So we mask out all but the last bit. And then we say, as long as it hasn't timed out, so as long as this result is 0, it means that is not set yet, wait. This is it's not an infinite loop, it's a busy wait loop. We keep asking, did you time out, did you time out, did you time out, did you time out, blah, 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 blah. So far, so good? So this is going to now fall through once that bit is set. So next thing we're going to do is we're going to do a store word IO R0, 0 R5. And the intention here is to go and set the timeout flag to 0. Means, okay, we saw that you reached a second. We did see that. Okay. But there is more seconds to count. So far, so good? So in the beginning of time, we started the timer. We said count a second, but do that continuously. So start for 50 million, count down to 0. The counter starts counting. We go into a busy wait loop. We keep looking at this indicator. The moment that indicator becomes 1, this means that the timer has reached 1 second. We go clear it because we asked the timer to do this continuously. It's going to count another second now. So we clear it. Next thing we do is we decrement the number of seconds we have to wait. And that, remember, is an argument to this function, Ri, R4, R4, minus 1. And we say, as long as this is not equal to 0, so there's still seconds to count, wait 1 more second. So we go back to this. Remember, the counter counts continuously. The moment it times out for 1 second, it reloads the 50 million and counts down again. So this is the inner loop. This waits for 1 second. This waits for as many seconds as we ask the function to wait for. Every time we find a timeout, we reset it. And that means we saw 1 more second, 1 more second, 1 more second. Yes, please.
Before you branch on the last one, then you need to move the R6 to R6 again?
2?
Don't you need to move 6 into R6 again?
No, because we said start and do this continuously. So the timer,
It already has the time.
yeah, the timer, the moment it times out, it reloads 50 million on its own and does that for you. So it really counts second in real time. It doesn't rely on you to go and reset it and do that. Well, you can do that, but there's going to be some jitter there, as they say. We're going to explain that in a second. Yes, please. R4 is the argument to this function, which is, so if you go down to the basement, okay, it's up here. Wait a second, integer argument, seconds. So you call this function, you say wait for 100 seconds. It's going to iterate 100 times on the outer loop, and who knows how many times in the inner loop, because this is busy wait. Yes, please.
Would we possibly miss 5 threads with that one?
What?
Like say if the timer didn't finish
Yes.
at the first line of the loop,
Yes.
but it finished at the second line of the loop.
Yes.
That means we kind of missed a few.
That's exactly why we asked. So the question is the following. We observe that the timeout has occurred via this instruction. Okay? This is executing inside my CPU. However, the timeout is a real-time event, and it happens at some point in time. The worst-case scenario, it just happens here in time, in between, right? So I have to do this, 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 and then I will observe it. Okay? And then I will go here. Okay? This is exactly why we use the continuous mode and timer, so that it resets itself and starts counting the next second without waiting for us to look at it. The continuous mode says, look, I'm going to raise my hand and said I time out. Whether you look at me or not, I don't care. I will count the next second. So the timer does that in real time. The moment the first second elapses, it starts counting the second without waiting for you to look at their raised hand. That's why you use continuous. If you haven't done that, there's going to be some, I think the right term for that is jitter. That is, an event has happened, but you take time to respond to it. That is variable time. Fine, it's not that much, but it's still something. So you're going to count time with some, what's the right term? It's not going to be accurate enough. Depending on the application, that may be an issue. If you're doing audio, maybe not so much because this is megahertz. If you're doing like video signals, obviously, I mean, you're going to see problems in your screen. Am I making any sense? Yes, no, maybe? I don't know what to make of it. Anyway, I will assume, unless you ask me, I will assume everything is okay, the wall is still in its place, and everything is wonderful, no problems. Okay. The counter is counting on its own without worrying whether we are looking at it or not. The moment we fired off this 6, whatever it was, the 6, we said it, keep counting 1 second. Anytime there is a second, raise your hand. If your hand is already raised, don't bother. Keep it there. That's it. Okay. And then we go and we look at it at some point. All we know is that since the last time we look at the hand that was up, at least 1 second has passed. That's what we know from the CPU perspective. Okay. Okay. However, the timer will religiously raise its hand every second without any worries about how the CPU reacts to it or not. So far, so good? Now at the end down here, we're done. We have to stop the counter. So we're going to do a store word IO R0 for R6. And then we can say return. Okay, we go to the status, to the control register, R5, sorry. This is our base register. We go to the control register. We set everything to 0. Done. The timer stops.
Should that branch be non-equal, right? Start for 0, 1 sec?
Absolutely. Because otherwise you're going to count 2 to the 32. Unless you call it with 1, you're going to count 2 to the 32, give or take seconds. And that's quite a bit of time. We're good? Okay, and that concludes the timer. If you have time, you want to play with it, you can connect a speaker to one of the PIT outputs, and then you can have the timer turn that on and off with specific frequencies, so you can generate sounds. Back in the 80s, that's where personal computers were generating sound. Anytime you hear this, old Nintendo games or whatever, that's typically what it is. It's just a speaker that goes up and down, not a nice sine wave or anything like that. It's just up and down, up and down. Any questions? All right, so we have 22 minutes left, which is good. I received an email over was it yesterday, today morning? I don't remember. Somebody was asking whether we can move the midterm. As I told you last time, I don't have any issues with moving the midterm. Okay? The question is, will that conflict with anybody else? Actually, it would be convenient for me to move the midterm so I can postpone writing one.
Same. We've got the exact same thing.
Yes. However, we do have to have a midterm because it's not a very good idea not to have one. Okay? Because you get a one-off to write well or not, and the exams take a big portion of this course. That's the bottom line. Okay. By the way, I did post all the exams today. There has never been an exam I didn't have a typo in, so I'm sure there are typos, and I knew them at some point. I haven't fixed them, so if something doesn't make sense, ask me. That's the easiest way. Okay. Now, question. The midterm right now is set for the 22nd or the 28th? I don't remember. 22nd. Okay, it's on the website. I know there is at least one person that wants to change that. Are there more people that would like to change that?
Yeah.
Yes.
Okay, so I see 4 people saying that I want to change that. Okay, 5 people that want to change that. That, unfortunately, is not a majority.
How about who doesn't want to change it?
I don't want to put people on the spot.
To what though?
Change to
The
what?
week after, because we have to
No, the week after.
So the suggestion was to do it on November 7th or something.
2 weeks after, 1 next.
2 weeks after.
Okay.
November 5th.
Okay, so November 5th, okay? The only complication with that, I will not be, you want to say something?
We'll have 2 midterms the same day if we need it.
You will have 2 midterms,
Yeah,
okay? On November 5th, okay, all right.
Will this like mess up the lab timings? Just like, were they designed so that the labs would correspond to what was taught?
Right now, we're okay with the labs. There is a large lab at the end, which is more like a project. And for that, we have to go to the second part of the course, which is almost about to start. The midterm will be up to this point. Whenever we take it, it's going to be up to this point.
I think like if we shift the next few labs a week early, would that be a problem?
No, okay, sorry, I was implying that no. It won't be an issue. I don't know how to do this. Look, the default will be the midterm stays where it is, and we take it whenever we take it. I know that there are some people told me that they have another midterm the very same day, and that creates complications. I am willing to, on a case-by-case basis, to say to somebody, you don't have to take the midterm, but then everything goes to the final. I honestly believe that's a horrible idea. However, if you insist, I don't mind that. It's going to be bad, though. I mean, no, it may be good, it may be bad. I mean, but I will tend to believe it's actually not a very good idea.
It's your choice to take the midterm?
Let me put it this way. If I put it to everybody over there, it's going to be... I would like to have a good reason from you why you would like to do that, and I would like to discuss it on a case-by-case basis, right? Can I make that a policy for the whole course? Actually, I couldn't care less whether there are grades on this course or not, but they have to be. Okay? So let's not go there. It's not a question of that. The way to set a standard for that is the following. If we were medical doctors and this was like, let's learn how to do open heart surgery, well, would you like to go to a doctor that never actually took an exam on it? Probably not. Okay, fine. We're not medical doctors. Okay, so we're not medical doctors, so it's not exactly the same level of seriousness and immediateness. However, we are engineers or computer scientists, and people may have an issue with working with somebody who has no clue what they're doing. So that's why the exam is a way of setting some standard. It doesn't say much, it just says what it says. It's some proxy for what your abilities are, right? This doesn't mean that if you didn't write the exam, you're not good, or it doesn't mean that if you wrote the exam, you're particularly spectacular or whatever. It just means that. That's what it is. I know how, it's just a metric that people can use. Okay. Too much stuff. Yes, miss?
It's probably going to very far-fetched here. It's probably not going to happen, but can we do it November 12th then?
Can we do it November 12th? Well, you're going to then have about a week left, a month left for the final. I'm okay with doing, I don't know how to handle this. You're a relatively small group of people. Do you have a way of meeting all together and somebody coming and saying, this is what we agreed? Next time I asked everybody, can you confirm, please? I'll give you a day. Can you confirm that this is what you agreed? And we can do that. I have no issue with doing this on November 12th. I think it's a bit too late with the schedule. Actually works pretty well for me because I'm going to be physically in Toronto at that time. November 5th, I'm not going to be physically in Toronto. I can't. So I won't be able to come to your exam. And also Alberto will not be physically in Toronto either.
Yeah, so you said November 12th is better than November 5th.
Okay. So please take some time and let me know, right? I'm going to write the exam. I will plan for the 22nd, we said.
Yeah. So,
which is very close. It's like a week from now, right? Oops, okay, but I can do that.
So, like, does everything in this part of the course wrap up this week then?
Yeah.
Sorry, everything?
Like everything for this part of the course, the first half of the course, wrap up this week,
Yes.
and all that could be on the midterm, right?
Yes.
And if we
Okay.
shift the midterm, it's still the same content.
Yes. Yes. Yes, yes, yes. Absolutely. Okay. No, I'm not. I mean, I think this is a good spot to say this is as much as you need to know. Everything is open notes, open books, open notes. Don't bring another person. Don't bring a communication device. You can talk. I'm not going to care whether you remember this number, right? I will care whether you know how to program that, but you do have the notes there. That's how people work in real life too, right? I want to know that you understand the concepts, right? You're going to see the midterms that are there. You're going to see what kind of questions are being asked. Usually, pretty much all the questions are, have you read and understood what's going on? Some of the questions are fairly straightforward, which really means that any mistakes you're going to make are going to be straightforward. And that's unfortunate, but that's the way it is, right? So you're going to be looking and say, how did I do that? Like I do all the time when I write on the board. But you're taking the exam, I'm not. Okay? I did that a long time ago. There may be one question that says, okay, you know all this stuff. Here's a problem you haven't seen before. What can you think? Now, the other I'm not quite sure. Let me say this at the end. Okay. Yes.
So since it's open book, we can bring both our lecture notes and your previous
Yes.
online notes?
Yes. 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 Yes.
And
Huh?
the labs.
Huh?
And the labs.
Everything. Okay. Well, I mean, anything you can carry and you can physically fit in the room, right? That's
Are we
the.
gonna need to know like how to interface with the Lego controller, or just like the timer for the I/O stuff?
I don't know what you ask me now.
Okay, so like there's the Lego controller.
Yeah.
It is just an I/O device, but are we gonna need to know like the specific registers for that device?
Extremely unlikely. I don't know them either.
Good enough.
Okay, I mean, if there is something there, it's going to be, okay, here's a device, it does this, program it, or something like that.
Okay. So you'll
Okay.
give us the
Yeah.
control registers.
I mean, look, the questions are going to be, I mean, here's a bunch of instructions, tell me what each instruction does, okay? Do you understand assembly? Okay, here's a data structure in memory, tell me how it's laid out. Do you understand alignment? Do you understand this kind of things? Probably write a function, okay? Do you understand how functions are being called or not? Okay, maybe here's a device, I mean, tell me how to program that. I mean,
It's not gonna be a simple bed mass calculator, right?
what, eh?
Not a simple bed mass calculator, right?
No, the question is not going to be, can you, look, this is not a course about algorithms.
Yeah.
It's a course about, let's learn how to program computers at a very low level and what are the ramifications of that. So if there is a question on an algorithm, I mean, I don't think I'm going to push it. I mean, there is interesting questions you can ask about algorithms, but this is not a data structures and algorithms course, right? We care more about the mechanics of instruction. I mean, a typical question that many people get wrong is if I execute a program, how many memory accesses happen, right? And you have to think what it means I do memory accesses. I have to fetch instructions, I have to do data accesses too, stuff like that, right? Okay. Anyway.
Can we bring the processor manual and?
Yes, yes. I think I've been clear. You can bring anything you want as long as it's not another person or a means of asking somebody else to do something for you. Is that a good definition? I don't know. Probably we have to form a committee to see if it is, but I think you get the message, right? Yes.
Something like this timer specification.
Yeah.
Is it like something like we should have on our cheat sheet, or like is this something that?
I tend to write, again, I would like to think that I tend to write exams where all the information you need is there. Now, will I give you the definition of an add die or move I? No. Right? I will assume you remember that. So again, I cannot give you a set of rules that say this is exactly the type of information that we use, but it might be, here's the timer, here's it, right? Okay. If you look at past exams, I don't think you're going to find many questions that have devices in that form. Remember what this does or whatever. Okay. Can we do this now? Maybe? We can try, see if we finish. If we don't finish, we're going to cover it some other time. It's a nice, I thought it would be a nice point to interject this topic we haven't covered. At some point, we have to cover that, in my opinion, so it would be nice to do that. If we don't finish today, I'll revisit at some other point. When we meet on Monday, I'm going to start talking about CPU design from this point on. So if you don't remember digital design, make sure you do, eventually. Okay?
Are you posting these slides?
I'll try to do so, okay? And I also wrote a lecture on lecture notes on viruses. I will try to post that. I gave it to Mustafa. Okay, now real numbers. We talked about integers. We talk about, that is signed numbers. We want to represent stuff like that. How do we do this with a computer? Now, again, primary school stuff, when you write this dot, what does it mean? Right, or comma if you're in Europe. These are powers of 2. For integers, these are all positive powers of 2. These are negative powers of 2. So this is 1/10, 100, 1,000th. So if you do this in binary now, it's exactly the same concept. Instead of having a base 10, you have a base 2. So this happened to be 2 to the 0, 2 to the 1, so forth. This is 2 to the minus 1, so 1.5 in decimal, 1/4, 1/12.5, whatever is that, so on and so forth. So if you were to take this binary representation and try to write it in decimal form, you'll get this number. And let's pretend that I did this correctly. Okay? All right, now, how can you represent this? There are some applications where, sorry, these slides have a lot of funny things, so I apologize for those. Anyway, long time ago. We all had better days. Okay. One way to represent real numbers to use what's called a fixed point representation. So here's a bunch of bits. So far for us, this was an integer, so this was 2 to the 0. Well, no, not anymore. You say, by convention, there is a dot there. somewhere. Let's pretend the dot is here. You don't have to physically represent that explicitly in the computer. You just write on the manual and you say that's what the number means. And all the circuits we have for addition, multiplication, blah, 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 for integer numbers work like magic for this, as long as you interpret things correctly. So in this case, there is a dot somewhere. It's called fixed point because you cannot touch this. You cannot move it around. That's what this means. So these two are fractional. This is 2 to the minus 1, 2 to the minus 2. Okay, that's what it means. So this would be a 4.2 representation. 4 integer digits and 2 fractional digits, right? And there is only so many numbers you can represent with that. Now, again, I told you it has this stupid graphics. Anyway, so a lot of computers, especially in the early days, they were using fixed point representation. And the idea was there that the person that programs these computers, they're extremely well versed in engineering, in math, or whatever, physics, whatever, and they can deal with this. So it's a programmer's problem, right? You want to express whatever problem you have 2 small numbers, you're going to use scale factors to do this kind of stuff. So you rewrite your equations so that everything falls within the range you can represent. Okay? There is another representation that people use today. That's one on another graphics. And this is the floating point representation. See, I told you. Okay, what does it mean, floating point? It means I have a bunch of bits now, all right? But as part of the representation, explicitly, I specify where the dot is. So I can use, for example, with 6 bits, I can represent something like that. I can also represent something like this or something like this. This is the intention. I will tell you how this is done. It's not done like this. This is so that you can get the idea. All right? So for example, if the dot is there, that number means 127. As we know, it's an integer. If the dot is here, this number will mean 2 to the minus something. So it's that number. Okay? That's the idea here. Now, this was done by a committee. The floating point representation, I think it's called IEEE some number, 8067, whatever it's called. But the idea here is the following. Sorry, I think I lost my train of thought. Okay, yes, okay. So I'll tell you what people have done. They said we have a bunch of bits. All right. I have a very large number. And now what I will do is I only have so many bits I can use to represent that number. I will do a compromise. I will compromise and only represent as much as I can. So let's say I only have 6 bits. I have these 2 numbers I would like to represent. In one case, this is a number that's a very large integer, right? It has so many digits. I don't remember how many there are, 16 or 32. It looks like 32, okay? Right. This is a very large number. And I also have this other number that's very, very small. You see that? Okay. The one is over here. However, remember, computers are finite things. So how many bits I will choose for my representation is going to be a fixed number of bits. Let's pretend I have 6 bits to do that. The idea behind floating point is to take your losses and not represent the numbers precisely, but represent them as close as possibly. And the idea there is the following. You represent as many digits as you can following the leading one. This is the idea behind floating point. So I have this number, and because I only have 6 bits of significance that I can represent, I'm not going to be able to represent the exact number you want. I'm going to be able to represent something that has these upper 6 bits, and everything else is going to be assumed to be 0. This is a compromise. So floating point representation is, by definition, not precise. There are only very few numbers that can be represented precisely. That was not true for integers. For integers, everything is precise up to some fixed range. All the numbers are described precisely. Here, that's no longer the case. You can represent a very large range of numbers. However, there is this concept of significance. That is how many digits of that number you can actually represent. And that's not as big as the range you can represent. So for this number, I'm going to represent this much. For this number, I'm going to be able to represent this. And the idea here is I would like to have a representation that will allow me to say, these are the significant bits, and this is where they start in the range of digits. Okay, you with me? Okay. Clearly, this is not a representation you want to use for your bank account. I mean, I hope you have this much on your bank account, but let's pretend we're dead. Let's say we're Bill Gates, whoever, right? You don't want that, right? 6 digits. I mean, sure, it's a lot of money still, but how about this? This is a lot. So it's not precise. You don't want that. Same thing here. Maybe this is more representative of our bank account, especially if you're a student or whatever. Still, I mean, why lose a few gazillions, like 1/1000th of a penny? It's not theirs to take. Long story short, here's the actual representation now. I'm showing you what's called single precision. Single precision is a 32-bit representation. There are other standard formats that are either 16, 64, or 128 bits. This was done by a committee. There were people back in, I think, late 70s, early 80s. It took them 10 years to arrive to this. It has its problems, but it's a standard representation. Most computers support this to some degree, some of them faithfully, but even the representation itself has some leeway on what operations mean. Long story short, you have three things here. The first thing is a sign bit, easy thing. This means whether the number is positive or negative. Okay? Next thing is the position of the dot. This is an exponent. So you take this and you convert the 2 to the e. Remember, when you're multiplying with the power of 2, you're essentially shifting the number. If you're multiplying with a positive power of 2, you're shifting digits. You're moving whatever you have in your hands towards this side. When you're multiplying with a negative power of 2, you're pushing it that way. That's why this is a representation where the dot is. Okay? This is called the exponent. Finally, you have the significant part, which is the mantissa. Mantissa contains the digits of the number you can actually represent with how many bits you have. In our case, this is going to be 23 bits. This is the precision or the number of bits that you are allowed to represent. Okay? Notice, however, that if I were to go back to my previous example, we said if I have a bunch of bits to represent, I will find the leading one and represent the rest. Floating point is a normalized representation. That is, the mantissa always starts with 1. For that reason, the way you interpret this number is 1 point that's not represented, the mantissa. Okay? Am I making any sense to you? Okay? I'm hoping you can follow what I'm saying. Not necessarily appreciate why it's like that. That's the way it is. That's the way to view it. As I told you, this was a committee. 10 years it took them to arrive to this, why this is a good idea. Okay, so without further ado, let's look at an actual number now, see how we can interpret it. It's not an easy thing to do. Okay. So let's say I have this representation, this 1, first bit. This means negative number. Next bit is the number 129. The exponent is actually a biased number. So it's an integer, however, you have to subtract 127 from it. So 129 really means 2. Why is it biased? It's a way to be able to represent positive and negative numbers. If you wish, it's kind of a form of a sign magnitude. This is the exponent part. This number, if you write it down, it's 120, whatever it is, 29, right? You subtract 127 because that's the bias as part of the definition of this representation. You get the actual exponent. So the number now is minus 2 to the second from this. And now let's look at the mantissa. The mantissa is this part. So the mantissa is 0.1, but we have the implied 1. So the number is minus from the sign, 2 from the exponent, 1, the implied 1, 0.1. So this is the number. Minus 6.
So the mantissa is flipped, the smallest number is on the left?
This, you write 1 point this, whatever that is. And you interpret it in binary. So it's 1.5 in decimal. Because this is 2 to the minus 1, 0.5. There's a 1 that's implied, 1.5. 2 to the 2 times 4, you get 6 and minus. Do you get a sense of roughly what this number means and how things are represented? Again, don't ask why it's like that. This is the way it is. And again, it's a compromise, so you can have some significant bits represented, this many, 23 of them, some big range of numbers, minus 120 whatever, to plus 20, 120 something else, right? It's a big range of numbers, very large, very small. And you can represent this many bits, positive and negative. Yes, please.
I'm not sure how you got the 1100
This is a binary number. multiply by 2 to the second. Okay, what does that mean? If you multiply by 2, you add a 0 here, so you shift this by 1 position, you multiply by 2 again, you get another 0. So this becomes 110.06. One more example, people who at the gates. I'll post this, okay? So,
I think you had a typo with the bottom of it.
what?
Can you go back?
I have a typo.
Yeah, it should be
110.0.
Yes, absolutely. Yeah, you're right. Okay. Let me fix that before I... Let me fix it. You guys are good.
Because you said 6. Yeah, that's not 6.
Absolutely. And as always, I wasn't testing you. Okay? Fair enough? Okay, so when I post these, look at them and see if you can follow that. Okay. Because I think it's 3 now and we cannot fit things. There is a bunch of slides at the end. You don't have to follow this stuff. There is some stuff over here that talks about it. The moment you see mathematical formulas, don't go. There is I can point you to a very long note. It's like 100 pages of one of the people that designed the standard that explains the reasoning behind it. At some point in my life, I read the first 20 pages. I got lost very quickly, right? There is a branch of computer science called numerical analysis, which says the following: I have a mathematical problem I wish to solve with computers. I understand that computers cannot represent arithmetic correctly. There are some issues with arithmetic, with math. How can I solve this problem and get a result that's close to what I wanted to get? It's a whole branch of thing. Last thing I want to say is when you do floating point calculations, it is additions that is the problem. Because you often enough get a very large number and a very small one, and you cannot represent their sum, because this requires to have the big number here, the digit, the other ones that are over here, and they don't fit in 23 bits. So when you do floating point calculations, it's additions that are going to be causing most of the trouble. This doesn't mean that the other ones won't, but additions are a disaster, so you have to be very careful. And mathematical properties do not apply. That is, A plus B plus C, it's extremely unlikely this will be equal to A plus B plus C, right? It does happen sometimes, but that's not the norm. Again, I may be overdoing with the way I say it, but it's the other way around. Okay, I think we got to go.